In the last few videos, we've been looking at questions on stationary points. In this video, we're going to continue that work and look at maximum and minimum problems in context. This topic is often called optimisation. They're real-world problems. An example might be that we wanted to minimise the cost of a project or maximise the space that we have. With all of these, they're generally wordy questions. We break them down, we set up an equation, we use algebraic manipulation if required. We then go ahead and differentiate to find a value that either gives us a maximum or minimum. We check it's valid and then come to a conclusion. So let's go ahead and start. In question 10, we're told James is making a pig pen. He has 240 metres of fencing and would like to make a rectangular shaped pen with the largest possible area. He needs to fence 3 sides of the pen as a wall provides the 4th side. The longer side of the fence is y metres long and the 2 shorter sides of the fence are both x metres long as shown below. So we've got the building here which provides the wall. We've got x, y and x. In part A we need to find an expression for y in terms of x. So we can see that we got x, y and x and we got 240 metres. So we can say now that y plus the 2x will be equal to 240 metres. All of the fencing will be used to maximise the problem. We need to express y in terms of x, so simply substituting 2x on both sides. Y is equal to 240 minus 2x. So that is y in terms of x. In part B, we need to show that the area of the pen can be written as a is equal to 240x minus 2x squared. So I'm just going to write now that the area is equal to the length times by the width. Therefore, we can say now that the area is x multiplied by y. This is where the algebraic manipulation comes in. We want to express the area in terms of one variable. At the moment, I've got both x and y, and all I'm going to do is substitute in. So we can say now that a is equal to x multiplied by 240 minus 2x. Multiplying this out, the area is going to be 240x minus 2x squared. That's what we were asked to do. In part C, it says, hence find the maximum area for the pen. Sometimes these questions are split up and it will ask us to find the value of x which maximises this. All we're going to do is look now at what value of x will give us the largest value of a. And for that we can say that dA dx will be equal to 0 for this max, so for a max. This is a nice straightforward quadratic equation, and as we've seen before, we could go ahead and complete the square. What I'm just going to do though is write dA dx. So dA dx, that is going to be 240 minus 4x. Setting this to 0, 0 is going to be 240 minus 4x. Solving for x, 240 over 4, x is going to give us 60. This is the value of x that maximises the area. So we're looking at now when x changes, what influence does that have on the area? So all I need to do is just simply write this in. Therefore, we can say now max area, so max A, will be equal to, and I'm just going to substitute this in. I can put it here, I can put it in the other one. It's going to be 240 lots of 60 minus 2 lots of 60 squared. What's that going to give me? 7,200. Let's put that for a calculator. So we got 60, and then let's make sure I've got that right. So 240 lots of the answer minus 2 lots of the answer squared, which is going to give 7200. So this now, the max area is 7200, and that will be meters squared. Now, if we were asked to prove that this was the maximum, we could do it by simply drawing a graph. But if this wasn't a quadratic function, we could say now for max, and we've seen this before, the second derivative, in this particular case, d2a by dx squared will be less than 0. So my expression for d2a by dx squared in this particular case, all we need to do is differentiate this once again. 240 will be 0, then we'll have now negative 4, therefore now it's a max. I could have drawn this, and hopefully when you see the graph you'll see exactly, and I think this one is a nice one to start with. So this now is going to give us a parabola. It's a quadratic equation. It's a negative quadratic, and we could draw it. Let's draw it up so it'll be symmetric, and it'll come like so, and it'll look a bit like that. So we've got 0, 0, just this is already factored, and then that's going to be 120, 0. So what we have then, the axis of symmetry is here at x is equal to 60. So the maximum point right here is going to be where x is equal to 60, and of course then this now is right here, this is our area axis. So this is going to give the max value. So the max value is just at this point, and that of course is for 7,200. So we can see how it works, and as stated, if you wanted to get some idea, what we're looking at is essentially this graph. Where are we going to now, which value of x is going to give us the largest value of a, and that's why we're looking at dA dx. So how is a changing as x changes? Remember, x is going to be varying, which is what we're going to use to find this value right here. So nice little question, maximum area at 7,200. We substituted in, as we only have one variable, because we did, just here, we did this one, used algebraic manipulation to put now this as a problem in x. Okay, question 11. A rectangular sheet of metal measuring 4 centimetres by 5 centimetres has a square of side length x centimetres cut from each corner and is made into an open top tank. In part A, find the maximum volume of the tank, and in part B, prove that the answer found in part A gives a maximum value for the volume of the tank. Right, let's draw a little sketch. So with this, what I'm going to do is just sketch this up. So this is going to be my tank, and then what I'm going to have are these in the corners. So these are going to be squares of x. They're not perfect squares, but hopefully it'll give you some idea. We'll move that one into place shortly. That one was a bit too big. So now these have side length x. Let's just put that one just here. So originally now, the total side length right here was 5, and this one was 4. What we're going to do is cut these out. Remember, x now is varying. We want that the graph that we draw, or the graph that we can use, is going to show us that it's varying. We need to also be quite careful with a problem like this, because it's going to give us values that are not valid. So this one here is x, this is x, this is x, this is x. So these are going to be cut out like so, and that's what we have. If we consider this length right here, this used to be 5. All we've got now is this side length from here to here. So it's going to be 5 minus the 2 lots of x, 5 minus 2x. That's now what would be left if I folded this up. A killer error student says that it's 5 minus x, but we got x and x, which is 2x. This one just here used to be 4. All we've got left now is this part right here. So we're looking at 4 minus 2x. So that is our expression. If I folded this up, and I'll draw a very, very rough sketch. If I folded this up now into a cuboid, or as we've got here, a tank, and we put the dimensions on, we've got now this height of x, and then right here, this one, doesn't matter which one we put on, we can put 4 minus 2x. You can, of course, factor that if you want, if you think it makes your life slightly easier, and this one of 5 minus 2x. So what we're looking to do is maximise the volume. Again, the question could have been split up, and it might ask us to find the value of x that makes it a maximum, and hence find the maximum, or it might just do it in one whole go. So let's now look at the volume. We know that the volume of a cuboid is simply now the product of the 3 sides, or the area of a cross-section times by the length. So it's going to be x, then we're going to have 4 minus the 2x, and then we're going to have now 5 minus the 2x. Again, you might want to factor that. I'm just going to go ahead now and just multiply this out. So what we're going to have then is we'll have x, then we're going to have, what's that going to be, 20 minus, then we're going to have minus 8x minus 10x, and then we're going to get plus 4x squared. So an expression for the volume, I'll just write it now the other way around. We've got 4x cubed minus 18x squared plus 20x. So what we're looking to do is find the value of x that will now maximize this volume. And you might think, well, that's going to be as small as possible because we want them as small as possible. But if we just consider that this tank would then become very, very shallow, in terms of its length and its width, then it would be. But what we're looking to do is find that point. Before we go any further, I'm just going to graph this up. I'm just going to draw this graph, and hopefully it will make you see some certain things. And you'll see that some values of x are not going to be valid. First ones we can certainly say are not going to be valid are those that are going to give us negative numbers for x. It makes no sense. We can't have a negative x as it's a length. So this is the graph. Now, what I'm doing here, this is v essentially. This is a volume. So as x varies, what happens to the volume of this? Well, we can see now that we're going to have this point right here as a maximum. And you might say, well, this is higher. But if we consider now this point right here where x is equal to 2, if we go back to this now, if x was 2, we'd end up with this length being 0. So as you can see, it's only valid for certain values. So what we're really looking at is this right here, this area of the graph, or the region of the graph. So this is what we're expecting. We're expecting that value of x to give us now the volume that's going to be a maximum, and that would be the maximum volume. So let's go ahead and use calculus to do that. So what I'm going to write now for max, so for max now, max value of x that maximizes the volume, we can say that the derivative of v with respect to x. So how is v changing as x does? This will be equal to 0. So let's look at this now. dv dx is going to be equal to 12x squared minus 36x plus 20. So 0 is going to be equal to 12x squared minus 36x plus 20. Now I could try and simplify this if I really wanted. What will it divide by? All of those will divide by 4. So what's that going to give? 3x squared minus 9x plus 5. Regardless, it's not going to be pretty. So we got this quadratic equation to solve. Now we assume that, or the person marking this assumes that we haven't looked at the graph. So let's use quadratic equation. So we're going to have 9, and then we're going to have negative 9 squared, which is 81, minus 4 times by a, which is 4 times by 3, times by 5, all over 2a, which is going to give me now 6. So let's look at these values. So that's the first one, 2.26. So if we look at this one right here, 2.26, again, not going to be valid. That gives us this right here as a minimum, but is it's certainly not valid for the question. So let's just put here, what we'll have is x, and we'll just get this one right here. So x will be equal to 9, so x is equal to 9 plus or minus root 21 over 6. X cannot be equal to 9 plus root 21 over 6. Therefore, what we've got now, so therefore, x is going to be equal to 9 minus root 21 over 6. That's the x coordinate that maximizes the volume. It's not the maximum volume. The maximum volume will come in when I substitute it into here. So if we just change this over now and we put the negative in, we end up with this right here. So that's my 0.73 just there. That's that value. So let's grab the calculator up. So if I just store that in, shift store A, and then we can put it in here to maximize that volume. So if we want, I can just write A, and then we're going to have now, in fact, let's just put this in. We'll have now A multiplied by 4 minus 2 lots of A, and then multiply that by 5 minus 2 lots of A. You could have put the answer, really doesn't matter. There we go, 27 plus 7 root 21 over 9, which is 6.56, correct to 3 significant figures. So max volume, and I would show my workings here, so max volume, once I've substituted that in, do show you full workings. I have on the calculator, but I would expect you to do that. 6.56, 6.56, and that, remember, we're working here in centimetres, so this is going to be now centimetres cubed. So centimetres cubed, and that now is given to 3 significant figures. So all I've done here is simply gone ahead now and plug these in, and that's what we get. Now if we go back to the graph again, this was our 6.654. So what did we have? Let's just put that on there. 6.564. So as expected, and that gives us the maximum. So if it just asks for the value of x to begin with, go ahead and do that, and then substitute in. Prove that the answer found in part A gives a maximum value for the volume of a tank. So what we're going to do here is d2v by dx squared. Now for max, so this will be less than 0 for max value, so max. So let's get an expression for d2v, so d2v by dx squared. That's going to be now 24x, so 24x minus 36. If I now go back just here, what we've got, recall A, so that's a value. So all I'm going to do is now 24 lots of A minus the 36, and that is going to give negative, so negative 4 root 21. So negative 4 root 21, once I've substituted in the value that I found on my calculator, which we know is this 9 minus, so 9 minus root 21 over 6. You need to show that in your working. So therefore now we can say this is a max value, it's a value that will max it out. And that's our proof. But again, do show full workings. So there we go. Nice little question, nice and logical. All we've done is done a bit of algebraic, set up an equation, differentiated it, set it to 0, plugged it in, checked it works, made sense of it, and left it there. Right, let's go for another one. In 12, an open top cylinder with radius r centimetres and height h centimetres is being made out of metal and will, I think that should be will, and is to hold and is to hold. I think we'll go for is and is to hold. Exactly 20 pi centimetres cubed of liquid. In part A, we need to find the length of the radius that minimises the amount of metal required to make the cylinder, and in part B, hence, find the amount of metal used. So this is a minimising problem. What I'm going to do is just sketch this up. This one is slightly more challenging, but what we're going to do is some basic maths and a basic bit of manipulation. So here is my cylinder. Assume it's a right cylinder. So that length is R, that length is H, and now we have an open top. What I'm going to do is get an expression for the volume. The volume here is going to be pi r squared, that's the end, multiplied by the height. So from this, it's going to hold now 20 pi centimetres cubed of liquid. So 20 pi is equal to pi r squared height. So let's put in the pi. So from this, we can see that 20 is equal to r squared h. I'm going to leave that where it is. What I'm now going to do is consider that we're trying to minimise the amount of metal required. The amount of metal required is the surface area. The area is going to be the base, which is a circle, pi r squared. Then we've got the curve section. If we consider now the curve section, and if I just drew this out, let's just put this on here. This is the curve section. We know that the circumference of a circle is 2 pi r. That's the distance round, and that height is h. So the curved surface area is 2 pi r h. This is the area. We're looking to minimise this. So at this stage now, this is curved surface area, and then we've got the circle. We're going to do a bit of algebraic manipulation. So I'm going to substitute in, because at the moment I've got area in terms of both the radius and now the height. We only want it in terms of either the radius or the height. In this question, quite clearly, the radius is the one we want. So what I'm going to do at this point, I've got two equations. I'm going to say that h is equal to 20 over r squared. Again, this is my algebraic manipulation, and we're going to substitute in here. Ultimately, what I'm looking for is the area in terms of the radius. Pi r squared plus 2 pi r, then we've got h, which is going to be 20 over r squared. Area is going to be pi r squared plus now 2, and then we've got now 20, so that's going to be 40. So let's go ahead and put that on. So we've got now, let's just put this in, that's going to be 40, then we're going to have pi, and now this is going to be r over r squared, which is 1 over r squared, or r to the negative 1. What I'm going to say now, for minimum, again, it doesn't matter whether it's a maximum or minimum, for minimum, dA dr will be equal to 0. I'm going to differentiate A with respect to R. So what we're looking at is what happens to the area of this cylinder as R changes. So dA dr. Pi is just a constant. Therefore, what we're going to get here is 2 pi r. All I'm doing is differentiating r. Then we're going to have now negative 40 pi, and then we're going to have r to the negative 2, or we can say that that is over r squared. I'm going to set this equal to 0 and divide this. I'll do it, in fact, I'll do it 2 steps. I'm just going to set it to 0, then I'm going to divide both sides of the equation at this stage by 2 pi. That's going to give me 0 is equal to r minus 20 over r squared. All I'm going to do at this stage is multiply through by the r squared, and that is going to give us that r cubed is equal to 20. So r is going to be the cube root of 20. That now is the value of r that is going to minimize this problem. So all we've got to do, find the length of the radius. The length of the radius is going to be now the cube root of 20. So if we just find that now, so in here, shift, and then we can do the cube root of 20. That's going to be 2.71. So r is equal to 2.71 centimetres, and that is given to 3 significant figures. At this stage, we simply need to find the amount of the minimum amount of metal used. So I've got an expression just here. Remember the area, so the area is going to be equal to pi r squared plus 40 pi over r. That now doesn't have h in it. This is a in terms of r, so I'm simply going to substitute that in, and we can find now the minimum amount of metal used. It's the surface area. So let's go ahead and do this. So what we're going to have is 2 lots of now. Let's just get the answer back. That's the answer. I'm going to store it as a. We're going to store that as a. What have we got? We've got now we've got a squared. So let's just do pi. So we've got pi, and then we've got now a, which we need to square, and then we've got plus now 40 pi. Hopefully the calculator will like this, it's not going to moan at me, and that is over a. So pi r squared plus 40 pi over r, and that is going to give us 69.44. So the area is going to be 69.4, and that will be centimetres squared. That is what gives it now a minimum. Okay, so that's what we've done. If at any stage you were asked to show that that gives the minimum value, we would simply now do d2a by dr squared and show that this is greater than 0 for a min. So for a min. I'm going to differentiate this again. So if I just I'll write it out. So it's dA dr is going to be equal to 2 pi r. Then we're going to have negative, so it's minus 40 pi r to the negative 2. So d2a by dr squared is going to be 2 pi, which is just a constant, plus 80 pi r to the negative 3, or we can say now over r cubed. We weren't asked to do this, I'm doing it for completeness. So we can say now when r is equal to the cube root of 20, d2a by dr squared is equal to, and I'm just going to sub this in. So we know that the cube, let's just get that there, that's the cube root of 20. If you wanted to find it again, simply stick it in there. That's what it is, and you can store it as what you like, shift store A, shift store B. So what I'm going to do now is simply put this in here. So we're going to have 2 pi plus, now we're going to have 80 pi. We can quite clearly see this is going to be a positive value, but I'm just going to evaluate the second derivative over this value cubed, which of course is just that value. So let's just put that in. I suppose you can actually do this mentally, couldn't you? And that gives 6 pi. So 6 pi, therefore it is a minimum. So that's what we've done. So as say, r cubed was 20, and that would drop out to give 2 pi plus 4 pi, which is 6 pi. So that's it. That's what we do, and nice and straightforward once we've seen the format. Lots of these questions like this: algebraic manipulation, differentiation, set it to 0, find the value which either maximises or minimises the problem, check it's valid, find the answer, and then justify it by taking a second derivative. The questions might be structured slightly different, but that is the general approach.